Assalamu alaikum. I welcome you to the 39th lecture for the series of lectures on advanced computer architecture. Today we will continue our discussion on to the input-output systems. The focus of our discussion today will be the trends in interconnects of input-output devices and the bus-based interconnects, and then we will discuss about the standards of the buses. Last time we discussed the difference between the overall performance of a computing system and the performance of the central processing unit. Here we noticed that the overall performance of a computing system is the measure of the throughput of the system. The throughput of the system is indeed very much influenced by the performance of the processor as well as the systems which are external to the processor, but they are connected to the processor. We also noticed that the effect of neglecting the IOs onto the overall performance of a computing system can best be visualized by using the Amdahl's law. As you know, that the Amdahl's law identifies that the system speed up is limited by the slowest component of the system. Therefore, this law suggests that the overall performance of a system must affect by the IO systems. Therefore, we cannot define the performance of a system without considering the performance of the input-output systems. Then we discussed what is an IO system. Here we noticed that an IO system comprises the storage IOs and communication IOs. The storage IOs consist of the secondary and tertiary storage devices, and the communication IOs consist of IO bus system, which indeed interconnects the microprocessor and the memory with the input-output devices. We also noticed that the developments in the processing system affected the storage industry also, and it motivated to develop, number one, smaller, cheaper, more reliable and lower power storages, which are usually referred to as the embedded storages. These type of storage devices are used in ubiquitous computing. And at the same time, we need high capacity, hierarchically managed storage devices which are to be used for data utilities. Last time, while talking about IO systems, we also noticed that the diversity, capacity, latency and bandwidth are the most important parameters of the IO performance measurement. Furthermore, the IO systems work on the principle of producer-server model, which comprises an area called Q wherein the tasks are accumulated while waiting to be serviced. Furthermore, the metric of disk I/O performance are measured by the response time and the throughput. The response time is in fact the time to queue and device service time, whereas the throughput is the percent of the total bandwidth. Now, whatever we discussed last time regarding the performance measurement of the I/O systems, let us consider an example and compare the performance of two different types of I/Os. For this, let us assume that the read and write time of 64K bytes block is to be calculated for the flash memory and for the disk memory, and let us see how it affects the response time, therefore the overall throughput of the system. Here we can assume that the flash memory takes 65 nanoseconds to read 1 byte, and say it takes 1.5 microseconds to write 1 byte and 5 milliseconds to erase 4 kilobyte of information. Whereas the disk storage has the average seek time equal to 4 milliseconds, the average rotational delay equal to 8.3 milliseconds, the transfer time is equal to 4.2 megabytes per second, and the control overhead is equal to 0.1 millisecond. With this data, we can calculate, first of all, the average read-write time for the disk. However, we must notice one thing, that the average read-write time of a disk is always equal, and it can be calculated as the sum of the average seek time, average rotational delay, the transfer time, and the controller overhead. If we substitute the values from the given data, the result for read-write time is equal to 27.3 millisecond. Whereas now if we calculate the read time for the flash, we must know that the read time for the flash memory is indeed the ratio of the flash size to the read bandwidth. Now, the given data shows that the flash size we are assuming is 64K byte, and the read bandwidth is 1 byte per 65 nanoseconds. This results in the read time for flash memory to be equal to 4.3 millisecond. So this calculation shows that the flash is about 6 times faster than the disk for reading 64K byte. Whereas now if we calculate the write time for the flash, in fact is equal to the sum of the erase time and the ratio of the flash size to the write bandwidth. We know from the given data that the erase time is given to be equal to 5 millisecond for 4 k byte. Therefore, for the 64 k byte, the erase time is 64 kb divided by 4 kb per 5 millisecond, and adding this value to the ratio of the flash size to the write bandwidth, the result is 178.3 milliseconds. This shows that the disk is about 6 times faster than the flash for writing 64 kb. So this is a very interesting result, which you can see that the flash is having a better performance for the read as compared to the disk, whereas the write has better performance for the disk as compared to read. So with this much discussion on to what is the performance of I/O system, how we can compare the performance of I/O devices, we will now discuss today the trends in designing and developing the interconnects. The I/O interconnect is the glue that interfaces computer system components together. The I/O interconnects are facilitated by using high-speed hardware interfaces and by using some logical protocols. Now, based on the desired communication distance, bandwidth, latency, and reliability, the interconnect types can be classified as the backplane interconnects, channels, and networks. If we look into the performance and the properties of these interconnects, the network interconnects are used where the distance is very large, that is, say, it is more than 1 kilometer, whereas the interconnects of type channel are used where the distance is between 10 to 100 meters, and the backplane interconnects are used for a very small distance. Normally, the backplane interconnects are those which are used to connect the backplane of a central processing unit or a microprocessor-based computing system with the external devices. Whereas, based on the bandwidth, networks basically are developed where the bandwidth is in the range of 10 to 100 megabytes per second, and the channels are used for 40,000 megabytes per second, and the backplanes have the bandwidth of 320 to 1000 plus megabyte. The latency of the backplane is basically lowest, whereas for the channels it is medium, and for the networks it is highest. However, the reliability of networks is low, and it is medium for the channels, and it is very high for the backplanes. Backplanes usually use the byte parity methods to achieve the reliability in the system, and it gives us a very high reliability. The interconnects are usually implemented by using the bus system. The bus is basically a shared communication link between subsystems. It is a collection of number of conductors where buses can be classified as the data bus, the address bus, and control bus. The data bus is usually used to have a two-way communication, that is, from the microprocessor to the memory or IOs, and from the IOs or memory to the microprocessor. Whereas the address bus is a unidirectional bus. The address is generated by the microprocessor and it identifies the location of the memory or IO device for data communication purposes. And the control bus contains number of control signals. The advantages of using buses are that the buses are low cost, that is, a single set of wires is used in multiple ways. The buses also offer versatility. They are easy to add new devices and peripherals even when they are ported between the computers, and they can be ported by using common bus. However, the bus-based interconnects have some disadvantages also. The major disadvantage of a bus is that it creates a communication bottleneck, possibly limiting the maximum I/O throughputs. In a server system where I/O is very frequent, the designing of a bus is very, very complex, and it demands that it must meet the challenges of enhancing performance of the processor. However, the bus speed is limited by the physical factors such as the bus bandwidth, the bus length, and the bus loading. The bus loading means the number of devices which are being connected to a bus. These physical limits prevent arbitrary bus speed up, which make the bus design difficult. Now let us talk about the classification of buses. Basically, there are two generic classifications of buses. These classifications are the I/O buses and the CPU memory bus. The I/O buses, which are also sometimes called the channels, they are lengthy and they facilitate to connect many types of devices, and they offer wide range in the data bandwidth and follow a bus standard. Whereas the CPU memory bus, which is also sometimes called the backplane bus, is in fact a high-speed bus which matches the memory system to maximize the memory CPU bandwidth, and usually it is used to connect single devices. Now, with this much introduction about the types of buses, let us see how bus transactions take place. The bus transactions are usually defined with reference to memory, that is, what they do with memory, that whether information is to be written into the memory or it is to be read from the memory. Accordingly, we say that the bus transaction is the read transaction or the write transaction. The bus transaction, in fact, includes two parts, that is, sending the address and receiving the data. Now, let us see how the read transaction takes place. For read transactions, the address is first sent down the bus to the memory together with asserting the read signal. And in response to this, the memory sends the data and it deasserts a signal which is usually known as the wait signal. Whereas for the write transaction, the address and data both are sent down the bus to the memory together with asserting the write signal. The memory stores the data and deassert the wait signal. Now, let us see what are the protocols which are used for the bus transition. The bus transition protocols, which are also known as the bus communication protocols, they specify the sequence of events and timing requirements in transferring the information. The communication is of two types, that is synchronous bus communication and asynchronous bus communication. The synchronous bus transfer is one which follows a sequence of operations relative to a common clock, whereas the asynchronous bus transfer is one which is not clocked and it uses some control lines such as the request line and acknowledge line. These lines, in fact, provide complete handshaking among the devices for a particular bus transition, which means that some signal is sent from the memory or from the CPU to the memory, and when the transition is complete, a signal is passed on from the device or from the memory to the processor. The timing diagram for synchronous bus protocols here shows that the address is transmitted in the first clock, and then using the control lines to indicate the type of request, the read begins when not read is asserted. Not read means that the read is active low. Here in this second diagram, you can see that the data is read and it is in the waiting state until the wait signal is asserted. Now, let us see the asynchronous handshaking protocols. Here from this timing diagram, you can see that the asynchronous bus is not clocked, rather it is self-timed. The handshaking protocols are used between the sender and the receiver. You can note it from here that in the beginning, at the time slot marked T0, the master obtains the control and it asserts the address, direction, and data. Furthermore, it waits a specified amount of time for the slave, which means the receiving device decodes the target. At the second time slots, which means when the first operation is complete, now at the second instance, the master asserts the request, and then at the next time slot, the slave, which is the receiving end, it asserts an acknowledge signal, and it indicates that the data has been received. Once the data has been received, at the time slot T3, the master releases the request signal, and then the time slot T4 shows that the slave releases the acknowledge. Here please note that the terminology master is used for the controller, which is controlling the communication or generating the request, and the slave is used for the device which is responding to this request. Here you can see the read transition for the handshaking protocols. Here at time T0, the master has obtained control and it asserts the address, direction, and it waits a specified amount of time for the slave to decode the target location. Now the master asserts the request signal, and it is followed by the slave asserting the acknowledge, which means that the receiving end now asserts an acknowledge signal. It indicates that it is ready to transmit the data. Once the slave has asserted the acknowledge signal, then the master basically releases the request, which indicates that it has received the data. Once the data has been received by the master, then the slave releases the acknowledge signal, and this way the whole transactions for the read operation is completed. Now, having understood the concept of bus transaction, the most important is to understand how is a bus reserved by a device that wishes to communicate when multiple devices need the bus access. This actually means that in a practical situation, when more than one devices are connected to a bus, let us see how the bus is being allocated to a particular device. This is in fact accomplished by introducing one or more bus masters into the system. A bus master is basically the one which has the ability to control the bus request and initiate the transactions. We use the terminologies bus master and bus slave. The bus master is one which is basically responsible to initiate the bus transaction, whereas the bus slave is the module or the device which is activated by the master for the desired transactions. In a simple system, processor is a bus master and it initiates a bus request, and memory is usually a slave. Alternatively, we can say that a system may have multiple bus masters, and each of which may initiate a bus transfer to the same slave. However, it is a very chaotic situation. This situation is indeed equivalent to the situation when in a class where the number of students are sitting, they at once start asking questions to the instructor. Now, in this example, basically, the students are behaving like a master and the instructor is behaving like a slave. That is, there is one device and there are multiple masters who want to use that particular device. Now, you can think of how the instructor will overcome this situation. The instructor must have to develop some protocols based on which the instructor will decide who is the next student to whom he has to talk. So, if we implement the same strategy for the bus control, there is a need of some protocols to manage the bus transaction by more than one masters. Now, these types of protocols are referred to as the bus arbitration protocols. The bus arbitration protocol provides the mechanism for arbitrating access to the bus so that it is used in a complete cooperative manner. Here, a device or a processor which is behaving as a master and it wants to use the bus, it signals a bus request and later on the bus is granted to it whenever it is available. And once the bus is granted, the master uses the bus, and when it is finished, the transactions, the signal is sent to the arbiter that the bus is no more required. The arbiter then may grant the bus to another master. The multiple master bus have a set of 3 control lines to perform all these operations, and these 3 control lines are known as the grant line, the request line, and the release line. With this much understanding of the bus arbitration, let us talk about the schemes which are used for bus arbitration. The bus arbitration schemes usually try to balance 2 factors, that is the bus priority and fairness. From bus priority, we mean that every device has a certain priority and the device with highest priority should be serviced first. Whereas the fairness deals with guaranteeing that every device must get the bus eventually, whether it is of lowest priority or it is of medium priority. The bus arbitration schemes are classified as the daisy chain arbitration, centralized parallel arbitration, and distributed arbitration. The daisy chain arbitration is one where the bus grant line runs through all the devices in a order of priority such that the line is running from highest to the lowest priority. You can see it from this diagram over here. Now here you can see that if the device has requested bus access, it uses the grant line to determine that whether the access has been given to it or not. The sequence which daisy chain arbitrator follows is that at the first instance it signals the request line, then it waits for transition on the grant line from high to low. This indicates that the bus is being reassigned. The third step is that it intercepts the grant signal and do not allow the lower priority devices to see it, which means that it stops asserting the request line. Then the fourth step is that it uses the bus, and the fifth step is it signals the bus is no longer required. When it finishes, then it signals that the bus is no longer required, and it signals this by asserting the release line. So by following these 5 steps, the transaction is completed, bus is handed over to the highest priority request, and then when it finishes, it releases the bus for the service of the next request. The centralized parallel arbitration scheme is one which uses multiple request lines. Here, the devices independently request the bus, that is, the arbitration is centralized and all the devices can send a request in parallel. The centralized arbiter chooses from among the devices, it requests the bus access and notify the selected device that is at present acting as a bus master. Once the bus has been allocated to the master, it starts using it, and once it has finished with the transaction, then it releases the bus, and this process is repeated. The third type of arbitration is the distributed bus arbitration. The distributed arbitration can be further classified into 2 types, that is, the distributed arbitration by using self-selection and by using collision detection. The distributed arbitration by self-selection also uses multiple request lines. Here, the devices requesting the bus access determine who will be granted the access. This means that in this particular case, it is the device which is going to determine who will be granted the access. Here, each device wanting the access places a code indicating its identity on the bus. So this means that if more than one devices want to have an access, they place their code. Then this code is examined by the arbiter, and the device can determine the highest priority device and it then selects the highest priority and hands over the bus to this particular device. And when this device finishes, it releases the bus, and then this process is repeated for the next request. The distributed arbitration by collision, in this scheme, each device independently requests the bus. Multiple simultaneous requests result in a collision. This means that when more than one devices make a simultaneous request, this is a situation of collision. Here, in the collision state, a device is selected among the collided devices based on the priority. Once a device has been selected, the bus is handed over to the device. Now, we have talked about the bus arbitration in detail, which is providing us the protocols for handling multiple devices which are making requests for a single bus. Now, let us see how we can make use of all of our previous discussion, that is the bus communication protocols, the bus arbitration protocols, and bus transactions. How we can make use of all this to decide about designing a bus. The bus design decisions are basically made on the basis of different attributes. These attributes are referred to as the bus bandwidth, data width, and transfer size. Based on the bus bandwidth, separate address and data buses are used for high performance bus architecture, while the multiplexed address and data is used for low cost designs. Similarly, based on the data width, wider buses, that is a 64-bit data bus, is recommended for high performance systems, and the narrow data bus, that is of 8-bit data bus, they are usually used as a cheaper solution for simple systems. Furthermore, based on the transfer size, multiple words are transferred for high performance systems, and it offers less overhead, while the single word transfer is used for low cost designs as it is simple. The other parameters which are also important for the bus design are referred to as the split transition and bus masters. Based on the bus masters, multiple masters are used in high performance computing, and single master that involves no arbitration is used for low cost systems. The split transition is used for high performance designs where separate request and reply packets get higher bandwidth. This technique, in fact, involves multiple masters. The synchronous multiple master protocol can be understood with the help of this timing diagram here. Here you can see that the multiple processors or the I/O devices can initiate the transactions. The bus can offer higher bandwidth using packets as opposed to holding the bus for full transaction. This technique which is also known as the pipeline bus technique, is very, very useful for multiple masters. Here, the bus events are divided into number of requests and replies. So, the bus can be used in the time in between a request and a reply from one master. The split transaction makes the bus available for the other masters while the memory is performing the read word from the requested address. Now, with this much discussion about the bus arbitration protocols and the bus design decisions, let us have a look into the bus standards. There are a number of bus standards which are in use at the moment. The most commonly used bus standard is known as the SCSI bus standard, where the SCSI, SCSI, stands for Small Computer System Interface. In this standard, the clock rate is ranging from 5 megahertz to 10 megahertz and then to 20 megahertz. Up to 10 megahertz, it is usually referred to as the fast clock rate, and the 20 megahertz rate is called the ultra fast rate. The bit is 8-bit or 16 bits, whereas the device can be either a slave, which means it may be a target, or it may be a master, that is an initiator. The SCSI protocols have a series of phases during which specific actions are taken by the controller and the SCSI disk. The series of actions are the bus free. The bus free action is one which identifies that no device is currently accessing the bus. The arbitration phase is one when the SCSI bus goes free. Multiple devices may request and they can be fixed for a particular priority. The other phase is called the selection phase. The selection phase informs the target that it will participate in the communication. And the command phase is one when the initiator reads the SCSI command byte from the host memory and it sends them to the target. The data transfer phase is one where the operations such as data in or data out are performed, and in this particular case the initiator is the target. The message phase is one where the message in or out, the initiator, the target, they all identify, save and restore data operations. And the status phase is one which identifies the target just before the command is complete. Today we have talked about the input-output interconnect trends. Then we discussed the performance of disk and the flash memory. We compared their performance. Followed by this discussion, we discussed the bus-based interconnects, and then we talked about the bus transaction techniques, wherein we discuss the read transactions, the write transactions, and then we discussed the bus communication protocols, the bus communication techniques such as the synchronous bus transfer and asynchronous bus transfer are also discussed. Then we talked about the bus arbitration protocols and bus arbitration schemes. Now, with this much discussion about the buses and the bus transactions, we conclude our discussion for today. Next time, inshallah, we will discuss the design of disk arrays and their impact on the performance of complete computing systems. Now, till next times, Allah Hafiz. Thank you very much.